This video will show how to measure dynamic range in Linrad, and also a little bit about how to select windows for the FFTs to get a good suppression of aliasing Spurs. And I will try to explain how these things work. The hardware is a pcie9842. It's a PCI Express card that can sample 14-bit at 200 MHz. So first I will set up the card, and that is A and K for the PCIe card. The rate dividend is the number by which the 200 MHz clock is divided. And I divide it by 1 to run at 200 MHz. I don't know anything about the clock error, so I feed 0 for the error. Resampling factor. Linrad can take average of samples and by that way getting a lower sampling rate. For this first test I will not make any reduction but run at 200 MHz, so I put 0 here. And I don't need any sound output. Well, I can put sound output anyway. So I select a sound card for the output, that is B, and use port audio, no, and the motherboard sound card, that is 0, and then X, W to save. I do the dynamic range measurement in the SSB mode, so I press D, and this is the first time for this sampling speed, so I have to set all the parameters. Press any key. The maximum FFT size is 32,768, which gives a bandwidth of 6 kHz. Setting something smaller here will not help. Best performance is obtained with another window than this one. It is the window number 9, which is a flat function with the Gaussian error function to go from 1 to 0 at the both ends. So it's 9. And 200 MHz is a very high frequency. I have to use the highest FFT implementation, it's 3. It is doing 4 transforms each time. The input is real data, so I get 4 complex transforms out for each computation. Now that's not enough. I have to go in here and say use 6 threads in parallel for this computation. Means 6 times 4, 24 parallel FFT computations. Storage time 0. At this high sampling rate, having a storage time will eat the memory quickly. This is a 32-bit implementation, so there is not so much memory. I don't have yet 64-bit assembly, so I cannot run this fast enough Fourier transform on the 64-bit version of Linrad. And then enter. I take the default parameters here. Well, no, let's make this number 8. That's a Gaussian window. It will give a more beautiful filter. And here we go. I press A for amplitudes, and you can see the signal I have is 1 dB below the point of saturation. I have a crystal oscillator at 14.16 megahertz about. I can click on the signal here. Oops. And use the wheel mouse to go to the right frequency. That is a spur. More about that later. Another spur. Another spur. There are many of them because I don't have an appropriate relation between sampling speeds for the selected FFT size. This is too slow. .16 is here. Now, Linrad is not quite capable of doing 200 megahertz sampling, that is 100 megahertz bandwidth, so there are occasional glitches. That's not a problem for the measurements I'm going to do in this video, but it would be a problem for real usage. Now, measurements are best done by use of the S-meter. I move things away that I don't need for the time. And here is the S-meter graph, which I will expand. Let's look here. I can expand this window a bit. Makes it easier. Like that. And then I go here for dBm, because there I have a calibration facility. I want to see the RMS value, so that is the yellow track, as you can see here. And I have to wait for a period of time when there are no glitches. It can run a little bit faster. Here, oops. It says minus 21.32. So I put here minus 31, no, minus 21.33. Enter. Now the graph shows 0. And I can verify that. You can see 0.00 something and the third decimal. We have a lot of spurs. I can make this a little bit narrower and then change the frequency with the wheel mouse. And you can see this spur is very strong. And this one also. It's only 3 dB below the main signal. This is because of the far too big resampling ratio. So I change parameters, that's X, P, and here, first mixer bandwidth reduction in powers of 2. I make it 10 instead. That means that the sampling rate will be 2 to the power of 10, slower than 200 megahertz, or rather than 100 megahertz, because now the format is complex data. So I click the signal again. 14 point. I can make it cover a wider range. Oops. And here now the calibration has changed. We have something completely different. I put 0 here to read now what we have. 17.565, so I feed 17.565 here to again read 0 for the signal. It is 0.0007 that I read, and then I can change the frequency to look for the Spurs. And sometimes things go wrong because this computer is now very heavily loaded. I click the signal again. Here is the signal at 0 in level. And here is a spur. It is minus 100 dB. Another spur, minus 100 dB. And the third one, minus 100 dB. The change had a dramatic influence on the suppression of aliases. There is a fairly simple theory for that, but I'm not going to go into it. I just show what's happening. So X, P, and then enter and enter, and I go here and put 9. 2 to power 9, that is 512. So 200 megahertz divided by 512, that is 200 divided by 512 equals 390 kilohertz. That's a fairly high frequency for the baseband, but this is necessary because the transform is pretty small. The bin resolution is 6 kilohertz, and that's a fairly wide bin size. This is a limitation in Linrad at this time, September 2, 2014. So again, I click at the signal and go to the main signal. which is here. Note that the calibration now stays at the same level, at least closely. You can see 0.005, which is good enough. The Spurs, to see them better, I will make this window wider, like that. The computer is heavily loaded. Things go wrong occasionally here. Let's look at it. I move this away so I can press T to get the timing. And you can see here 90%. This is part of the first FFT, the power computation. I can make this smaller by not computing the power, that means waterfall and spectrum, for the entire frequency range by clicking here. This is the third overtone, I want to see that, but the load is a little bit smaller, and hopefully malfunction will happen less frequency now. Let's have a look at the CPU load. That's top. (563%). But there are 8 cores, so the maximum is 800%, presumably. Quit that and have a look at the load on the processors, the speed that they actually have. That means copy pros info to something, and then look at that file. And we can see the first CPU is running at 3.6 gigahertz. The second one also. The third one. Fourth one. The fifth one. The sixth one. The seventh. And the 8th. All processors run at the maximum speed. But we're not showing the entire spectrum. This machine is fast enough to not very often have any problems. The 2 Spurs, this one and that one, they are not resampling Spurs. We can see that by stepping in frequency. If they have been resampling, I would have expected more of them at a constant interval. This could be a resampling Spur. Maybe or maybe not. I don't know. Anyway, Spur levels are low now. Here is something. And here are several Spurs of unknown origin. But Spurs is not really a problem. A good operator can avoid them. There are few really very strong signals, so there are not many Spurs originating from them in a real life situation. So I go back and have a look at the close range here. I want to measure the sideband noise. To do that, I expand the frequency scale here in the baseband graph to maybe like this. It's 1 kilohertz from here to here. Means that I want a bandwidth of, let's say, 1 kilohertz for the measurement here. So this much is about as that much. To check, I grab the BFO and measure the frequency here, 170.36. 171.36. The filter is a little bit too wide, so I make it a trifle narrower. Oops. Maybe like that. 171.33. 17.33 is here. Well, like that, I think. 70.38. 71.38. This is good enough. A very small error on the bandwidth makes an extremely small error on the noise floor measurement. So the signal, it has to be at, oops, 1, was it 158, I think. Here. And it's still at 0 dB on the S meter, as we can see. 0.014. Well, there is a small change. I can as well fix that. 0. And then I read what we have. 17.58. 17.58. And now we should read 0 with 3 decimals. There are close range Spurs. Presumably that is phase noise on the sampling clock of this card. There are some glitches, which is not a big concern. The frequency now is 14. Well, I moved the BFO to the signal, so the frequency of the signal is 14.158.6. So I step 10 kilohertz away from here. 168.6. This is close enough. And look, what is the level here? About 113. So I get it with some precision like that. Minus 114.57. So that means that the noise floor is 30 dB below this in 1 Hertz bandwidth. That means 144.6 dBc per hertz. 144.6. And this is at the separation of 10 kilohertz. So I can go to 100 kilohertz away, that is 14.258. That's too far. 258 here. And the noise is a little bit lower. That's not very surprising. It's 118.4, means we have 148.4 dBc per hertz at 100 kilohertz. And if I go 1 megahertz away, here, the level goes down very little. So 119.9, that means 149.9 at 1 megahertz. So sideband noise is low for this card. One should expect that. It's not a cheap card, it's rather expensive. The dominating spur is the third overtone. It's up here. I click it like that, and I don't want to have a narrow filter anymore because it's easier to look here. It is suppressed by 80 decibels. I cannot say for sure that this is a distortion in the PCIe card. It could be also third harmonic from the low pass filter I'm using to get rid of overtones from the oscillator. These are mini circuits filters. There could be iron in them. They could give the third overtone. This is something I don't know. I will now change the settings for the pcie9842 X, X, and U, and A, and then K. And as before, I used the 200 megahertz sampling rate, but I will now enter a resampling factor. Let's make it 2. It means that the clock is divided by 4 for a sampling speed of 50 megahertz with a 25 megahertz total bandwidth. X, X, W to save, and then D again, and now the sampling speed is 50 megahertz. Now everything is much easier. Again, I select the fastest transform, but I don't need to run 6 threads in parallel. Let's make it 2. I'm not sure, but well, make it 3. And by default, Linrad selects this very high bandwidth reduction because Linrad believes that I'm using a bigger transform, which I cannot do here at this rather high sampling speed, but that will be changed with some coming version of Linrad. And this window, best to use 8. Then enter, and here we are. And now the total bandwidth we can see is 25 megahertz, of course. So I press T for timing, and things look far better. And there are still glitches. We are still sampling at 200 megahertz. So the PCI bus is working hard. So I click on the signal. And it should be 14.158, I think. Here. We have strong Spurs, of course, because we still have this very high bandwidth reduction. So I go back, looking at the Spurs. This is the main signal. It's a little bit different from before because we have made some real changes. So I put 0 and check this 21.19, and then look at the spur, the resampling spur. Was going too fast. That's the signal, and here is the spur. I make the bandwidth a little bit narrower to be sure I don't get anything else. And now you can see that even though the resampling is 12, means 10, 2 to power 12, the suppression of the resampling spur is no longer 3 dB, it's 43 dB. X, P, and I go here for, let's say, 10. And look at again the signal. So the signal is here at 0, and here are 2 spurs. And these spurs come at regular intervals. These are the resampling spurs. And the level is in the order of 100 dB. Oops. Oh. And you can see when the strong signal is moved further away, they become stronger. And then they go down again. So it's a peculiarity. The strongest are in the order of 72 dB. So I need to make the bandwidth reduction bigger. X, P. I'll go for 9 here. And there is the signal. X, P, and here is my mistake. This is now a sine squared window, which is not very good. This should have been 9. And now things are different. Here's the signal. Which is at 16.46, 16.46. And I step away a little bit. Here is the step size, which I control with a depressed mouse, with a depressed mouse wheel. And here is a spur, which I don't think is a resampling spur. It's that thing that belongs to the sound card, to the PCIe card, or it could be something with the test oscillator, if it picks up something. But it's clear. Here are two spurs, close spaced. This one is, I don't know what that could be, but probably something with the computer or the FPGA in the PCIe card. So this looks very good, doesn't it? Here comes the signal. And I want to measure sideband noise again. So this one let's make it, probably it is still 1 kilohertz. 158.05, 159. No. Like that then. 159.08. 158.08. This is good enough. Here is the signal, and I step 10 kilohertz away from it. 14.158. That becomes 14.168. Here is 10 kilohertz away. And we have some glitches and problems, but not too many. I can look here. 114.27 means that the sideband noise is 144.3. That's pretty close to the value I saw without this averaging. It should have been the same, but now I got 144.3 and the previous time I got 144.6. And that is perfectly okay, because here you can see RMS, that means the standard deviation for a single measurement here is 0.6 dB. Now I made 100 measurements, which means that the error should be about 10 times smaller, or 0.07 dB. And the error we have between comparing two measurements was 0.3 dB. A little bit too large, but not a big issue, I think. So I think I have shown a little bit how this works, and now I will make a change again. Now I will set up the PCIe card differently. That is A and K, and I tell it to divide the sampling clock by 4, like that, and not to do any averaging within Linrad. That's 0 here, and then X, X, W and D. Now the sampling speed that Linrad sees is the same, but the pcie9842 is sampling at a 4 times lower rate. So if I look at the signal, 158 here, it's close but not exactly the same. I don't know why. Let's see. Sorry. 17.57. 17.57. And then the noise floor 10 kilohertz away. 14168. Here. This is 112 and plus 30 dB for the bandwidth means 142.1. 42.1. This is a degradation by 4.3 to 2.1. That's only 2 decibels. So we didn't see any loss nearly, because this is at the close range where sideband noise from the sampling clock is the problem. So I go 1 megahertz away instead, that's here. And here the noise floor is minus 114.4, which translates to minus 144.4 dBc per hertz. When sampling at 200 megahertz I had 149.9. So it means there is about 6 decibels degradation of the noise floor, which is in accordance with theory, sampling 4 times slower.